This lab is very simple. So what we're going to do, so we're going to study resistance, resistor connection actually. Okay, experiment number 4. So we're studying resistor connection. There's two types of resistor connection, right? You can connect serially, serial connection, and then we can connect resistors parallelly. Okay. Parallel connection. So you know the idea of these two. Yesterday also we discussed what is the idea of serial connection and parallel connection. Serial mean all the items should be on one single line. So the resistors generally, there's two type of symbols in circuits. You will see some textbook they use just a box like that to represent the resistor. The most of the textbook actually standard symbol is this kind of zigzag line. Okay, so that's the standard symbol for the resistor. Both are fine depending on the textbook and the instructor. They may use either, but I'm going to use the second version. Okay, this one to represent the resistor in our circuit diagram. So you can see the picture on page number 1 on your lab manual. Serial means all the resistors should be on one line. In this experiment, what we're going to do, we're going to take 3 different resistors, let's say R1, R2, R3, and we're going to connect it serially. And there should be a switch, and I should have a power supply, like the battery. So I have a battery voltage. Usually we writing VDC, or sometime you will see just E symbols to represent the battery. Switch is S. When you close the switch, so the continuous loop will set it up. As a result, so the current will pass through this loop, right? If I have a serial circuit, same current passing through every resistor. So if you take a look the voltage, then the voltage you can see divide into sections, right? So the each item in this serial circuit has a voltage drop. That means resistor 1 has a voltage drop of V1, resistor 2 has a voltage drop of V2, resistor 3 has a voltage drop of V3. Then all these voltages should be adding up to the given voltage, that is VDC. Make sense? Any question? Good. Then we can apply Ohm's law. Everybody know Ohm's law now? Ohm's law mean if you have a resistor, if you measure the voltage and current through the resistor, those two should be proportional to each other. So that proportionality constant is what we call the resistor. We should be equal to IR, right? That we discussed in detail last experiment. So we can apply Ohm's law for each of this resistor component. If you apply separately for the resistor 1, that will give you V1 is equal I times R1. Current is same through every component. If you apply for R2, V2 is equal I times R2. If you apply this for R3, V3 is equal I times R3. Now, if I consider the effective resistance out of all of these three, that means that resistance we call the resultant or equivalent resistance, right? So that means instead of 3, if I consider I have a larger resistor, so out of that 3 equivalent resistor, that should technically represent effect of all of those 3. Set it up with the same circuit, VDC and switch and R equivalent. Now if you apply the Ohm's law for this one, by applying Ohm's law, I will get same voltage, total voltage V, which is equal same current, I passing through there, but R equivalent. Now you know, on the other hand, addition of all of these voltages must be equal to V1 plus V2 plus V3 must be equal to the given voltage V, right? These two should be the same. So then you combine all of these equations together, right? So adding this one into here and each one of them into there. Then you will get an equation look like this. I times R equivalent which is equal I times R1 plus I times R2 plus I times R3. Then I is common, cancels out. Then I will get R equivalent, which is equal R1 plus R2 plus R3. So that is equivalent resistance for the serially connected resistance, which means generally you can write when resistors are serially connected, equivalent resistance is sum of all the resistance adding together. Make sense? So we done the similar concept yesterday for the capacitance. If you have a capacitance serially connected, remember this equation is opposite, right? This is actually 1 over addition if it is a capacitance, okay? So keep remember those things. Those are very simple mistakes, can happen during the exam too. Okay, question. So that's what we're gonna test during this experiment technically, okay? Now let's see if I have a parallel connection. Parallel means all the items should be connected. That's the important thing, right? If you have a serial connection, serial mean all the items should have same current, right? So that's the basis for the serial connection. If I have a parallel connection, which mean all the items should have to have a same voltage, right? So that's the basic difference between the serial and parallel, which mean if you want to connect resistors parallelly, I should connect all the resistance to the same voltage. So I can add all the resistance top of each other, R1, R2, R3, and then connect all these lines together and then get the output and then set it up into the outside voltage. Now this is the VDC, voltage add, switch. When I close the switch, current will pass through here, large current I. But when it come to a junction, then this current will divide into sections, right? So the current will be I1 through the R1, I2 through the R2, I3 through the R3. So now you can see the voltage is same through all of these resistances, right? Same voltage because two endpoints are here, point A and B is connected to this outside voltage VDC. However, the current is now different, right? You again apply the same condition, which is the Ohm's law for each resistance. If you apply for R1, you will get voltage across R1 V1 is the outside voltage V, which is equal I1 times R1. Voltage V is equal I2 times R2. Voltage V is equal I3 times R3. Now, if I consider out of these three, there should be some sort of resultant resistance, right? These three will act like a single resistor, so that is actually called the R equivalent. If I draw the diagram for equivalent, I'm going to have some single resistance connected to the same voltage given VDC switch. Now this is representing R equivalent, which is actually effective resistance of all these three, right? Let's apply again Ohm's law for this one. Then the same total current passing through here, same outside voltage, I times R equivalent. Now this I right here, you can see dividing into three sections, which mean the large I, which is equal I1 plus I2 plus I3. Now you connect again all of these five equations, right? Which means the large I, which is equal voltage given divide by R equivalent. Each of the I can find here. I1 is equal V over R1. I2 is equal V over R2. I3 is equal V over R3. Then you add all of those here. Then you will get V over R equivalent, V over R1, V over R2 plus V over R3. Then V cancels out. Then you will get R equivalent is equal 1 over R1 plus 1 over R2 plus 1 over R3 parentheses negative power 1, which means if you have a parallel connection, equivalent resistance is equal sum of all the resistance adding inversely then you have to get negative power 1, because right here you can see this is 1 over, right? So the 1 over, you invert one side of the equation, so you have to invert other side, okay? That represent by the negative sign. Okay, question. So these two equations, yesterday we done for the capacitance. Remember, the capacitance, these two are flip, okay? If you have a parallel capacitance, the direct addition. If you have a serial capacitance, then it is an inverse addition, okay? Question. So that's what we are planning on testing today. Technically, very simple experiment. So if we know the values R1, R2, R3, we can actually calculate by using this equation. Then we can measure by setting up a small circuit, and then we measure voltage and current. Then we can calculate each of the resistance by using the Ohm's law. And then from that angle, we can calculate the effective resistance too by knowing the voltage and total current passing through the circuit. So that call are measured, right? Technically, I can say R equivalent here is equal V given divide by the I passing through the circuit, right? So this is actually what we call the measured value then. So we can measure directly the voltage and current through the circuit. Then we can actually calculate R equivalent by using measured values. Then we can really calculate by knowing the R values. That is actually called the calculated value. Then we compare these two in the experiment. The same thing we're going to do for this circuit also. By knowing V and I, we can calculate R equivalent the same way. R equivalent here, V over I. Then we're going to compare that to the direct calculated value by knowing the R1, R2, and R3. So that's the plan. Okay, question. No problems? Okay, then the last part of the experiment, we're going to study this very specific type of circuit called the Winston bridge. So the Winston bridge is what? That is actually usually 4 resistances connected, 2 serially and another 2 serially, and then combine those 2 parallelly, right? So I can set it up a circuit like this one. I need to have one resistor here serially connected to another resistor, let's say R1 and R2. Then I need another 2 resistance connected, one here, R3 and R4 serially. So this is R3 and R4. Then this should connected to the outside voltage along this line. So now you can see there's a junction here. So I can connect this with another resistor or voltmeter or bulb, light bulb or anything like that. So let's apply a voltmeter here. Now let's say this end is A, this end is B. Then you can see R1 and R2 serially connected, R3 and R4 serially connected, and R1, R2 combination of these two parallelly connected to this. Okay, so that exact diagram is actually called the Winston type circuit. Now what we're going to do, so we're going to fix R1, R2 and R3. Those values we're going to fix. R1, R2 and R3. We're going to fix those values. Some random numbers. Okay, you can fix any number. Doesn't matter technically. Then we're going to use R4 as a variable resistor. So the R4 should be variable resistor. So the variable resistor generally marked in circuit this way. Okay, so a small symbol for R, but you're going to put an arrow here. That arrow represent variable resistor. Okay, now this is a variable resistor. So what we can do, since this is a variable resistor, means the value you can change, right? So if you can change this R value until you will see this voltage right here in between becomes 0. So that's the plan. So you change R4, we have to change R4 until voltage across, let's say these 2 points are C and D, until voltage between C and D becomes 0. When at that point, when that voltage becomes 0, then that point is called the balance point. So we call that, we balance the Winston bridge. Balancing means If you have these two voltage as zeros, mean there's no current passing through this line C to D, okay? Which means, this means that there's no current on the line of C to D. Voltage zero means there cannot be any current, right? Remember that. That's very important concept, right? Because current means the electron passing through one point to another point, right? So if you want to bring electron one point to another point, you have to do a work done, right? So the voltage is actually the energy. So you have to supply the energy to move electron one point to another. If you don't have any voltage difference, that means there's no energy. So you can't move the electron. So that's the idea. So if you make this voltage difference is zero, that means voltage exactly at this point is equal to voltage exactly at the other point. So that means there's no current passing through there. Good? Any questions so far? No questions? Okay, then we can apply Ohm's law again to this circuit. By applying Ohm's law, we can show that the ratio between these resistances R1 to R2, which is equal R3 to R4. So that's the one we're going to check by creating the Winston bridge. So if the Winston bridge is really balanced, that means if the voltage between these midpoints are zero, there's no current passing through that line. At that point, these ratios must be the same. Otherwise, Winston bridge cannot be balanced, right? So we know that must be true. By knowing that, what we're going to do in the experiment, we know R1 and R2 and R3. Those values are fixed, which means we know those numbers. By knowing those numbers, we're going to calculate R4. That call R4 calculated value. Then in the experiment, what we're going to do, we're going to set up a circuit by knowing these three values. Then we're going to change R4. We're going to change R4 until we see VDC equals 0. Until that voltage is 0, we're going to really observe that behavior. When that happens, we're going to take that number that we call the R4 measured. Then we're going to compare these two numbers together like we done for the previous two cases. If those two are the same, then we can confirm this equation is actually true. That's the idea. So we're going to confirm whether this is actually true behavior or not. Okay, question. No questions? Okay, then let us start, I think. It's nothing else to discuss as a theory. So it's very simple concept. Let's continue with the simulation. You can click on this link right here on page number 2. Then you will get it into the simulation page. Should be look like this. Let me reset everything here. When you initially get it into the simulation, that's going to be look like this page, right? So there are going to be two selections. You can click any, doesn't matter which one you select. Then you have those selection again here, just below this page right here. Then you can actually go vice versa. There's only small difference between the intro and lab. When you go intro, you can see there's no wire resistivity change selection tool here. Otherwise, everything is there. So the select the lab, but we are not using any wire resistivity. That's the one we use last experiment, right? So the last experiment, last part, we apply the wire resistivity and then recheck the resistivity effect of the wire. So in today's experiment, we don't need that. Get rid of that. Battery resistance, we don't care the battery resistance at all. And you can see here, right-hand side, two icons. You can click the battery. Then you can see all the items look like the real life scenario. If you click the circuit symbol, then you can see all the items, symbols are changing into the circuit symbols, okay? So then you can identify how each item is represented in the circuit diagrams. Okay, questions. Everybody have this simulation. Any questions so far? Good, no questions? Okay, then let's continue. So what we have to do, I'm going to keep first this real life battery like symbol to see all the items, how it look like in real life scenario. And then later, after you set it up the circuit, you can click the circuit symbol and then see how the real circuit should look like in circuit diagram scenario, okay? All right, so let's build a circuit for the case number 1. We need a circuit to represent the serial resistance. So we are studying 3 resistance connected serially, table number 1. So let's select 3 resistances. You can see the resistor here. Click and drag. I need 3 of them, right? 1, 2, and 3. And I need a battery. And we need a switch, right? And also we need ammeter to measure the current, right? Ammeter to measure the current. And we need the voltmeter to measure the voltage across each resistor, right? So we need voltmeter to measure voltage across each resistor. Then we connect these 2 endpoints. Then you have a continuous loop. So the circuit must be continuous to get the current, which means as far as the switch is on, now you can see there's no current passing through. Current is 0. Whenever you switch on, it will starting to pass in the current, right? And you can see right hand side, if you click this icon, you can see real circuit symbols for each of the item in the circuit, right? So that's the difference. So you can do either, doesn't matter. So I will keep it this one. Now, to change the values of these resistances, if you click on the resistance, you can see that highlighted with this yellow line. Then just below here, the icon appear. You can see right now all the resistances are same. So we'll change into a different numbers, right? First one will use maybe like 15 ohms. First one use the 15 ohms. Second one will select maybe 45 ohms. And third one will select 65 ohms. Okay, so now I change the resistances. Then you can see this color code are changing now, right? You see the resistance has a 4-line color code, right? So that's the another way you can measure the you can know the resistance value by knowing the line of the color code values of these lines, right? First line is actually number at the first, second line is the number at the second place, then the third line represent the 10 to the power value, 10 to the power 0, 1, 2, 3, 4, and then so on. Then the fourth line is actually represent the error. So if you know all those values for each color, then we can actually know easily what's the value of resistance. Okay, and the voltage, let's keep it 9 volt. We don't need the high power here. That's good enough. If your circuit is fine, then you can click on the switch. If you click on the switch, circuit will continuous. Then as far as you have continuous loop, now you can see current is passing through, right? Very small current because we have actually large resistance values there. That's why the current is fairly so small. Okay, 0.07 amps passing through each of them. Okay, let's change these values a little bit to the lower values to see how much the current is. Let's change this one into 25 and let's change this one into 35. Okay, now you can see current is fairly larger. Now it is 0.12. It's still very small, right? 0.12 amps. So I mentioned earlier too, during some time, session during the voltage. So the voltage is not actually what is dangerous in the circuit is the current. So if you have a DC voltage with the car battery actually can produce more than 10 amps. So if you have more than 10 amps passing through the body directly, that can kill a person. So the current is the most dangerous thing, not the voltage itself. If you have a high voltage and then if you isolate it and then touch the high voltage, the current will not pass through the body, right? Nothing will happen. But if you have a continuous loop through the body, large current pass through, that will kill the person. Okay, so let's continue. Now we have the circuit. Now the plan is that we know how to calculate the effective resistance by using the equation. So the plan is to measure the values and recheck the effective resistance. Let's use these three numbers. I think these three numbers are better because then you can see measurable current, or we have to improve the voltage. Let's see if I improve the voltage to 12, what will happen? Maybe we can use 15 because we need a fairly good measurable voltage and the current, both of them. Okay, let's do these numbers. Voltage will apply 12 and then the resistance will apply 15, 25, 35. Okay, so those are the numbers. So let's build all these tables on Excel sheet like we done earlier. Experiment number 4, table number 1. Table 1, you have to name it accordingly. Remember that if you have a table, make sure you name it accordingly. Table number 1, what we are studying, serial resistor circuit. Serial resistor circuit analysis. So the table number 1, right here, compare to the given table on your lab manual and then build exactly same table on the Excel. That's very simple. So I need the resistor values, right? Serial resistor values, R values, R1 and R2 and R3. All those numbers you have to write it down here. First circuit, this asking you to make a circuit between only R1 and R2. Then the secondary tasking the circuit between R1, R2 and R3, right? So the first circuit is just R1 plus R2. R1 is equal, we are selecting 15 ohms. I'm going to use ohms here, but remember you can actually always put that ohm symbol by using the insert button symbol here. If you go into the symbol, you can easily insert the ohm sign, okay? There, then you have the ohm sign. Oh, I think, wait, you mean the Excel sheet, right? Okay, now it should be good. Okay, yeah. Okay, so what I was telling earlier, set it up the table according to the given table on the lab manual. So the resistor number 1 is 15. Resistor number 2 is we are using 25, right? 15 and resistor number 2 is 25. Okay, and then we are studying that resistance circuit first, right? The first circuit is only between resistor R1 and R2. Let's change this very quickly. I need only 2 resistance. Click on any of the connection point and the scissor will appear. Cut that out. I don't need this one right now because I need only 2 resistors in my circuit. Okay, there you go. Now you have a serially connected resistor and the first circuit is between R1 and R2. Okay, so I need the voltmeter to measure voltage across each resistance. Bring this voltmeter here and then leave it like that. So if you connect negative side relative to the negative side of the battery right here, positive side relative to the positive side of the battery here, then you can measure the voltage across resistor number 1. If you bring that according to the second resistance, then you can measure voltage across resistor number 2. So those are the numbers we need. The current passing through the circuit is the same, right? Let's go back and take a look at the table. So the table, I need current passing through the circuit, voltage across each resistor, resistor values measured by using V and I, calculated values, and the percentage difference. Okay, let's build that table here first. So the voltage we are applying 15 now. Voltage we are applying 12 now. And the resistance values are 15 and 25. Okay, good. If you take the battery automatically, the battery set it up into a 9 volt. So I change that into a 12 volt. Okay. All right, then let's continue. Now what we need in our table, we need to have exactly same table like on your lab manual. So I need the current passing through the circuit, current, and then I need voltage across each resistance, voltage across each resistance. Then I need resistor values measured by resistor underscore, let's say, measured values by using V and I. And then keep, remember, you need the unit for all of these things. So I'm going to keep another layer here to represent the units. Okay, this unit's going to be ohms, and the current going to be unit of amps, and the volt going to be unit of volt, and the R measured going to be unit of ohms again. Then it asking you to calculate equivalent measured value, R underscore equivalent measured resistance, then R underscore equivalent calculated, then percentage different. Okay, all right. Formatting is up to you, right? I just showing you how to format maybe for one table. The rest of the table, I'm not gonna spend time on doing the table. You can do that later. Okay. So the formatting is should not be a big deal right now. Everybody should be familiar. All of this is stuff. Okay. So let me get rid of this PowerPoint, because if I share many things, sometimes this not let me to work on Excel sheet properly. Let me get rid of the PowerPoint. Okay, so now should be fine. Okay, so let's continue. Now what we need is the voltage and the current across each resistor, right? So you go back to the simulator. So the current is already there for the both resistors have the same current, 0.3 amps. This also has a 0.3 amps. Now we measuring the current down to 2 decimal places, right? So you have to format your table accordingly, okay? Battery is set to 12 volt. Okay, now let's take a look. So how much is the voltage across resistor number 1? Bring the voltmeter, probes across the resistor number 1. It is 4.5 volt. Just type that for R1 and then change the probes of the voltmeter to the resistor number 2, and the voltage across there is 7.5. Good. Any question? And you have to reformat this one, right? So the resistance we measuring down to three significant figures, down to 2 decimal places. You can format that column itself to represent that. Then you measuring voltage down to 2 significant figures, format cells. I need 2 decimal places to represent that correctly. Okay, now we have exactly right decimal places. Then we'll measure resistance for each one of the resistor by using measured voltage and current. You know, by applying the Ohm's law for each voltage, resistance is equal V divided by I, right? So that's how we're going to measure resistance, which means equal sign measured voltage divided by measured current. So I got 15. So you do the same thing for the second one. I got 25. So the percentage error going to be 0 for this kind of experiment, right? That's the bad part doing with the simulation. So always you will get the perfect result. Okay. Good. Any question so far? Good. No questions. Okay. Then let's take a look how to measure the R equivalent. R equivalent measured you can do by assuming if these two resistors acting as a single resistance, then the R equivalent you can measure by knowing the voltage, total voltage applied to the circuit and total current passing through the circuit, right? So the total voltage applied to the circuit is 15. Total current passing through the circuit is 0.3. So if you do that, R equivalent is actually 50 ohms. So that's what we're expecting because you apply 25 and 15, right? So R equivalent calculated, you know R1 plus R2. Let me write it down equation here too. This is R equivalent. This you can measure the voltage over current, but you have to consider total voltage, okay? Here we total applied divide by the total current passing through the circuit. R equivalent calculated is actually simply sum of all the resistor values, that means R1 plus R of 2. So that will be 50 again. So the percentage difference technically is 0. There's no meaning even doing that. Okay, good. Any question so far? So very simple calculation, okay, should not be any problem with this experiment. So the calculation should be very simple, and if you're doing it with the Excel, I think you can save time because later you can copy paste this whole table into your lab report without any problem. Good. Any question? Everybody okay? No problem. Okay, then let's continue to table number 2. Say it again. What is your question? What did you use for volt 12 means what? Oh, wait. This part. Yeah, yeah. So this should be 25, 15, 40, right? This should be 12 divided by 0.3. 12 divided by 0.3, and then this should be 15 plus 20 should be 40. Yes. It's still the percentage difference here. Okay, good. Yes, good point. The resultant resistance should be only 40 because we are applying 25 and 15. Good. Okay. Everybody okay with the table number 1? Let's continue to table 2 then. Any other question on there? Everybody know how to do the percentage difference and everything, I think. I did not calculate even that, there's no meaning, okay? And let's format this one too to represent 3 significant figures, right? So that's what we're measuring. So which means all the calculated values, you can represent 3 significant figures, okay? You're calculating here 3, this one has 3, that means all of these format cell to represent 3 significant figures. Good. So you can format each cell by cell, each column by column, or all the things in the table together. Okay, but I think it's better to format each column by column. Okay, then you can represent easily 3 significant figures for everywhere. Okay, so any question? Everybody okay with that? Okay, let's build this same table for 3 resistances. Let's build a circuit for 3 resistances first. So all we need to do is get rid of this endpoint right here and then bring another resistor, and then let's change that resistor value into, first one is 15, I guess, right? Second one is 25. Let's apply third one to 35. Third resistor is 35, okay? You can apply any number you like, but make sure you write it down properly, okay? You don't need to go exactly these numbers. If you want to apply different numbers, that's fine, okay? Okay, third one is 35. Now you can see circuit is connected. Usually, if you're doing this in class, there are certain precautions we have to do, right? Before you do anything to the circuit, we have to switch off first, disconnect the voltage and battery, and then you disconnect this point and add the new resistance, then you switch on and then measure all the numbers, right? But since it is a simulator, it doesn't matter, those safety precautions. Okay, then again, now for second case, we have 3 resistances, right? So now we have 3 resistances. The first 2 are the same, right? First 2 are the same, but I need the third one, or 3, which is now 35. This ohm symbol you can copy paste here, okay, as it needed. Okay, then we have to measure again. Current across the whole 3 of them is same, 0.16, 0.16, 0.16, because it's serial. Voltage will be different. You have to measure voltage each of the items separately. Right, let's measure that. Voltage across resistor number 1, 2.4. 2.4. Voltage across resistor number 2, 4.0. Voltage across resistor number 3, 5.6. Okay, that's all we need. It's very simple. And 5.6 here. And format this, all of these to represent 3 significant figures, right? Format cell. 3 sig figs means you can put 2 decimal places, then you will get into 3 significant figures, right? All good. And then let's calculate R by using measured values, right? R measured means that we're going to calculate resistance, but by using measured voltage and current. To do that, you have to equal sign measured voltage divide by measured current, right? That's all. Then you click and drag, So if I did measure everything correctly, I should be getting exactly expected result, right? Expected result is R1 15, R2 25, R3 35. It's a perfect result because it's a simulator. If you do this in class, you will never get this kind of result, okay? Let's format this one. Format that column also to represent three significant figures, which mean at least one decimal place to represent three sig figs. Then our measured equivalent mean adding these three numbers together, right? You can add all of these three together. You will get the expected result again. Adding these three together, you will get 75. Now to get the R equivalent, you have to add R1 plus R2 plus R3 given values, right? So the given values, 15, 25, 35. So you will get 75 again. Make sure you format cells to represent three significant figures always. And then the percentage difference is going to be 0. There's no meaning really even doing that, right? So that's the bad part doing the experiment this way. You will get perfect result. Okay. So that part 2 with the three resistances. Any questions so far? Everybody okay? Any question so far? And then you have completely done for table number 1. Then in your, let me write it down, the word here, resistors. Resistor. So always when you do the table column name should be a proper name. Okay, you can't just put R there. That's not really meaningful, and it should be a proper name. And then below that you have to put all the units for every single column. Okay, that's important. So this is also ohms, and R equivalent also ohm. You can either type unit ohm, name ohm, or you can just put the symbol, this omega. Okay, either one is fine. Percentage usually in percentage sign. There's no units there. Good, any question? And also, if you doing this calculation for your in Excel, when you do the your lab report, don't put the Excel equation like this equation right here on your data section. Instead of that, all those equations should show up on the appendix C. Okay, so don't add them into the table directly here. Instead, copy this table itself to your data section, data analysis section on your lab report. Then show all of these equation, how you've done the equation and everything on your appendix. Okay, that's the easy way. And then otherwise, if all of those equation also show here, if you copy paste that table into the table data analysis section, it's not really looks nice. Your report going to be looks bad. Okay, any question so far? Everybody okay? Then let's continue to parallel circuit. Let's build the next table, table number 2. Table 2, what we do in parallel circuit analysis, right? So you can just say parallel resistor circuit. You can name any way you like, right? It's just a name of the table. You can name any way you wish to name it, but make sure name should be meaningful, okay? Table 2, we do in parallel circuit analysis. So again, I need, it is right here. All of the columns are done. Table number 1. What was your problem? Ali? Okay. All right. So let's continue. Then parallel circuit again, the same thing. I have to do parallel circuit twice just by using R1 and R2 first, right? So again, the same thing. I have to have a resistor. I think, copy paste these directly, except the values, right? So the values will be different. Technically, the table will be the same. So, okay, let's get rid of the numbers here. Okay, so the first circuit we're going to do by using R1 and R2. Second circuit we're going to do by using three of them. The difference here is that when you have the parallel circuit, voltage going to be same. Because of that, first column will use the voltage in unit of volt. Second column will do the current. So I'm making the table exactly as it is on your lab manual. Okay. Current in terms of amps. Okay, so that's it. Then let's build that circuit first. So I need now parallel circuit, right? To build the parallel circuit, what we're gonna do? So let's get rid of this. Let's disconnect all of these. Click on any connecting point, then you can see scissor appear. Then you can actually get rid of. We don't need the third one here. And also one other thing you have to do, you have to take a picture of each circuit, right? If you read this information just above the table, you can see calculate the total resistance for the following serial combination, include a picture of each circuit diagram with all component at appendix C, right? So which means you have to take the screenshot of each circuit, okay? Before you disconnect, make sure you take that screenshot. Circuit should be properly connected. All the information should be visible, and those screenshot add them into the appendix C. Okay, you don't need to include them in the data analysis section. It's better to put them in the appendix C, or you can actually add them into procedure section too. That also fine. Apparatus and procedure section also fine. Okay, because you have to include little bit of procedure for each circuit. Then you can write serial circuit, picture of that, and then how you build the circuit, and then parallel circuit, picture of that, how you build that parallel circuit. Values mean the current and the voltage, at least for one of them, should be visible. Okay, you can't show all the values because technically you can put like 3 voltmeters and then show up all of them, but that is not necessary. Okay, complete circuit should be visible with values of the ammeter right here, and then voltmeter at least for one resistor. Okay, you can connect the voltmeter across one resistor at least, and then that value should be visible. Okay, then we know circuit is working fine when you're doing the experiment. Okay, question. All right, so let's build the parallel circuit then. Okay, so the parallel circuit means the two resistance should be go parallel like this, right? Parallel to each other, like this way. And let's bring two wires. One more wire here. And let's do the same thing on the other side. Okay, now you can see current passing through loop number 1 above, and now you can see current passing through the loop number 2 above. Okay, now these two are parallel to each other. Parallel means each resistor should be connected to the same output voltage, you can see. And then the other resistor also should be connected to the same output voltage. Okay. All right, so question. Now we have a parallel circuit for case 1. Now when you measure in the current for the parallel circuit, this current is not this current is also important, that is the total current, but we need the current passing through each resistor, which means I need to break this point here. I have to apply two another ammeters across each resistance, right? Since this is a simulation, you can bring any number of items without any problem. If this is a real life experiment, we don't have ammeters and voltmeters that many. We're gonna have only one ammeter for each group, right? So which means if I want to measure current passing through resistor 1, my ammeter should go on that loop, right? That will show you current passing through that resistor. If I want to have the current passing through the second resistor, ammeter should go here, right? So then you can connect these loops again. Okay, now we have same circuit again like earlier. Now you can see ammeters. I put actually 3 ammeters now, right? Because it's a simulator, we can have any number of items as we wish. But if this is an in-class experiment, you can't have actually 3 ammeters. Each time you have to break this point right here and then put the ammeter. Ammeter should go serially, right? That will tell you the current. And voltmeter can go parallelly. Now, if you measure the voltage across this resistor, voltage across that 12 volt, you can see input voltage is 12 on the battery. And if you do the same measurement across other resistor, it's still 12, right? So now you have a complete circuit diagram for two parallelly connected resistors. Question. Good. Okay. We have more freedom since we actually doing this in simulator, but if you're doing this in experiment, real life scenario, you don't have this much freedom. So you have to be very carefully disconnect and then connect these ammeters to get the right current passing through each of the loop in your parallel circuit. Okay, then let's write it down the numbers now. Okay, voltage across each resistor, now we know 12, right? There's no difference on there. And the current passing through each of the resistor is now different. Resistor number 1, I have 0.8 amps. Resistor number 2, we have 0.48 amps. Then, like earlier case, we'll calculate the resistor by using measured voltage and current. Voltage divide by the current value, and I got 15 ohms, that's the correct number. Second one, I got 25 ohms, that's the correct number. And let's reformat this voltage column here to represent only 3 significant figures. That means if you put 1 decimal place, that will be 3 significant figures. Our equivalent total is addition of these two, right? You can add those two together, sum of these two. Cell number 1 plus cell number 2 will give you 40. R equivalent total means adding these two given numbers, right? 15 and 25, which is also 40. And the percentage difference is 0. That column has no meaning any longer. Okay, question. Good? No question? Okay, then let's build the second circuit. I need another resistor. Should go parallel to these two, right? So let's build another parallel line with the third resistor. Okay. And also you can check the, if you click this icon right here, you can see the circuit diagram, right? With the circuit symbols. And if you click the battery sign right here, then you can see all the items as a real life scenario. And this small negative particles you can see moving around, those are actually the electrons, will show you the direction of current. If you want to get the conventional direction of current, you see opposite to the electron motion, right? So you can click on right hand side very top. You can see the icon says the electron or the conventional current and labels, and you can show all the values of resistances and then so on. So it's better maybe to click all of them before you take the screenshot. And also there's another way to measure the current. You can see here this one. This is actually a wireless ammeter. If you bring that close to a resistor, that will show you the amount of current passing through each of them. So which means instead of using these ammeters again and again, I can use this wireless sensor if I want to, right? Keep it right here, bring the sensor, and then you can see 1.62, 0.8, 0.48, 0.34. So you can measure these any way you like, doesn't matter, okay? And the voltage across each one gonna be the same. It should be 12 volt. All of the resistance are connected to the same battery. Okay, question. And make sure you take in the screenshot for each case, okay? No questions? Okay, then let's continue. Okay, then let's continue. Let's complete the table number 2. Table number 2, we know the voltage across each. Now we are on circuit number 2 on table number 2, right? Voltage are same, currents are different, 0.8, 0.48, and 0.34. Okay, and then let's calculate. This is 12, this is 0.34. Let's calculate the resistance. You know, voltage divided by the current. Voltage divided by the current for each case. 15. Second one should be 25. Third one should be 35. Now you can see for the third one, I'm getting a little bit of error. That's better actually, right? So that's actually good. So we need to have some error. Now, if you add all of these three together, then you will get the resultant resistance by using measured values, adding cell numbers together. That's the resultant resistance. Then to get the expected value, you have to add R1, R2, R3 together, the given values, right? R3 together. Then you will get the given answer, that is adding 35 plus 15 plus 25, right? 15 plus 25 plus 35, those are given numbers, you will get 75. Now you have a little bit of percentage error, you can calculate that. Equal sign, percentage difference means absolute value, parentheses, expected, minus what we got, divide by the average. Average means adding these two together. We calculating percentage difference, not the error, okay? Divide by 2, multiplied by 100. So I'm getting about like 0.1 percentage difference. So we can put percentage sign here. Okay, question. Good, no question? Any questions? Okay, make sure you take the screenshot before we moving into a next section. Now we done table number 1 and table number 2, okay, all the calculation, and then let's continue to table number 3. Table number 3, you have to make new two circuits, and it says R1 and R2 serial, and then R3 parallel to them, right? So let's make that circuit first. Get rid of all of these. And you can disconnect all of these, disconnect the circuit first. Okay, so we'll get rid of this one too. Okay, now I need R1 and R2 serially connecting to each other. R1 and R2 must be serially connected, okay, and then that should connect here, and then R3 should be connected parallel to those two, okay, should be look like this. Let's add another ammeter here, then I can actually find the current passing through that loop directly. Another ammeter there. Okay, good now. Okay, question. Don't need that one, so we can connect these directly. Okay, now R3 should be parallel to other two, right? All right. Now let's switch on the circuit. Then you can see current passing through and all the current values for each of the segment of the circuit loops. And also the voltage I can measure by using the voltmeter. Okay, you can bring the sensor to check the current again if you want to. Instead of applying the ammeters directly, you can use a sensor. And the voltage now I have to measure across R1, R2, and then R3 separately. Okay. Good, any question so far? So that's the circuit number 3, table number 3. Table number 3, first circuit. Okay, R1 and R2 serial to each other, and R3 must be parallel to those two. Okay. All right, so let's build table number 3. Okay, question. Anybody have any question? It's again going to be about the same table, so you can copy paste if you want to this table. It's not really anything big difference. It's about the same table, but there are very slight differences between the resistances. Okay. Let's get rid of these two. Okay, and then get rid of all of these numbers we had earlier. Those we don't need from the previous table. We have to calculate new. Okay, good. So the voltage apply is 12. That also not correct. We have to get rid of that. Okay. Resistance values you can keep it same. It's fine. And let's build exactly the table number 3 as it is. So I need voltage across each resistor. Current passing through each resistor are measured by using V and I, are equivalent by using measured values, are equivalent calculated, and percentage difference. Okay, good. So now R equivalent is not just simply R1 plus R2 plus R3. That you have to change. because now you can see, now you have to analyze this first, right? Because you can see R1 and R2 are parallel to each other. R1 and R2 are serial to each other. R3 is parallel, right? Which means our calculated is not the same. So the resultant resistance are actually different now. If you want to analyze that, so that have to do separately, that analysis part. Let's take a look how to get the result and resistance for this one. So that's important. So the case 3, this is table number 3, part 1. R1 plus R2 goes serial, and then R3 is parallel to each other. So it's going to be look like this now. R1, R2, R3 here. So the R1 and R2 look like adding together, R1 plus R2, but R3 is look like here in parallel because of that effective resistance, or the R equivalent gonna be equal to 1 over R3 plus 1 over R1 plus R2 negative power 1. Okay, make sense? Good, any question? So you have to do the effective resistance this way for the new circuit. Okay. And then later in case 2, it asking R1 and R3 serial to each other, R1 and R3 serial to each other, and R2 now parallel with them, which means now again R1 and R3 will add them together, then R2 parallel with that. Because of that, if you do R equivalent gonna be 1 over R1 plus R3 plus 1 over R2 negative power 1. Okay, this is for table number 3. Okay, good, any question so far? Everybody okay? Okay, then let's continue. Now, which means when you do this R equivalent calculation, you have to do it carefully. Okay. Okay, now let's write it down, all the measured values first by using the circuit. Okay, I need voltage across each resistor. Resistor number 1, voltage across this one is 4.5. Voltage across resistor number 2, 7.5. Voltage across resistor number 3 must be 12, right? Because they're directly connecting to the input voltage. So that should be 12. Okay, we have that. Then we need current across each of the resistor, right? Resistor number 1 and 2 has the same current, 0.3 and 0.3. Resistor number 3 has 0.34. By using those numbers, I can find the measured resistance values, which is equal sign voltage over current value, 15, 25 and 35.3. Only third one we have a little bit of error. That's okay, that's a rounding error, because you can see ammeter only showing you 2 decimal places, right? So that's the problem. So otherwise you will get exact number. Okay, good. Any question so far? Okay, now let's calculate this one. R equivalent calculated value. Equal sign, parentheses. I need 1 over values, right? So I need 1 over R1 plus R2 1 divided by parentheses R1 is 15 plus R2 is 25, close parentheses, close outside parentheses, and then add parentheses 1 divided by R3 is 35, given value, okay, close parentheses, close the outside parentheses, and then power you can put shift and 6 hat, and then I need -1 power. Hit enter button. You will get the effective or the resultant or equivalent resistance calculated value. Okay, equation so far. Everybody got that number? Everybody know that equation, right? You have to practice that yourself. The equation is right here, okay? So that's the equation for the equivalent resistance for the case 1, circuit number 1. Okay, good. Question? No question? Okay, how to get the measured effective resistance or the measured equivalent resistance? That you can do by knowing the total current passing through the resistances, all the resistances, total current passing through is actually 0.64, adding these two currents together, and the total voltage across whole circuit is 12, right? So I can do this measured value equal sign, and total voltage is 12 divided by the total current. Total current passing through is 0.64. So I getting 18.8. So there's a small error, that's a rounding error. Otherwise, we should get perfect result in this simulation. You can calculate the percentage different equal sign, ABS, parentheses, expected minus the calculated, close parentheses, divide by the average between these two, one plus the other, divide by 2, multiply by 100. So let me copy paste. Yeah, so let me copy paste that equations, then you can refer them later. All right, for this one, how I did this calculation right here. I will copy paste that equation into here, okay, this place. Okay, that's the formula we're using for that. And don't add this way to your data section. Okay, when you do the data section, make sure your table should not have this equation directly showing there. That actually makes your data table look bad. So that is not what we generally do if you're making a report, right? You're not showing all those information directly in your analysis section. Instead, put all those information into Appendix C. That's what the appendixes are means. Appendixes show all the detailed information about your report, but the report section, real analysis section should show you very brief results, okay? Only the table with the calculated values. Okay, this column, everybody know how to do that. Total voltage over total current. Total voltage over total current, and then the percentage difference. I think everybody familiar how to do this kind of calculation now. Okay. Maybe I should add these separately here, then you can refer it later. Table looks bad if you actually add all of them here. Okay, now let's get rid of this line. And let's reformat this one to be looks really nice table. Okay, now this one is for R, equivalent measured. This is R equivalent measured, right? R equivalent measured means equivalent resistance. Equivalent resistance means total voltage divided by total current passing through the whole circuit. No, not that. Total current passing through the whole circuit. Okay, total current passing through the whole circuit you can see on this top line. That's the total current passing through the whole circuit, or you can add these two numbers together. Okay, that is 0.64. And the total voltage applied to the whole circuit is 12 volt. This is the idea. If you have this circuit, if you have all this circuit is converted into this circuit, then what is the total voltage and the total current in this circuit? So that's what we're doing, okay? So the R equivalent is equal total voltage across the circuit divided by the total current. That is applying Ohm's law to the equivalent resistance, okay? Good, any question? Okay, good. What is your question about table 2? Anybody have any question? I is right here, total current. Total current is 0.64. You have to observe that from your circuit. Go to the circuit and then observe the current passing through the top line. Current passing through the top line is actually the total current. Okay. And also make sure you format all of these to show three significant figures, okay? Because all your measured values are up to three sig figs. We can't show anything more than three significant figures. Okay? So you have to format this cell by cell in some columns, otherwise you will not get three sig figs accurately, okay? Now you can see I am formatting this column number 2. First two cells I formatted separately, third one I formatted separately again because third one has 12 volt. If you set it up all of them into two decimal places, you will not get the right way, okay? All right, question. Or you can convert everything into scientific notation. Then you can format each column same way. If you're setting up into the scientific notation, the formatting going to be easy. But if you do in decimal places, you may have to change accordingly. Okay. All right. Any questions so far? So let's do this second circuit on table number 3. So are you still on table number 2? Are you still on previous case? This one right here? Oh, wait. Yeah, there's a mistake on that calculation. Let's do that quickly. Table number 2, parallel circuit. This is 1 over, right? So let's correct that. That's a good point. This should be 1 over. Parallel circuit R1 and R2. R1 should be 1 over. Parentheses 1 divided by this calculated value. Close parentheses. plus 1 divided by this calculated value, second R2, close parentheses, close outside parentheses, power minus 1. Okay, now you should get the right answer. Good. That's a good point. Everyone else is still in the table number 2. You have to take a look table number 2. Okay. You have to take a look the table number 2. All of these numbers you have to correct because table number 2 is the parallel circuit, which means these two should give us the same, but you have to calculate here. Okay, you can't just in the previous table number 1, I add them directly because it's just direct addition, very simple. But table 2, I can't do that. It's inverse addition. Okay, you have to do it carefully. Percentage different right here, it doesn't matter actually. It will calculate you the same way because it's a multiplication and division. Doesn't matter, you can add another parenthesis there if you want to. Will not be any difference at all. Okay, let me complete this table number 2 actually. So let us calculate this one again. Parent equal sign, 2 parentheses, 1 over 15 plus 1 over 25, close parentheses, power minus 1. Okay, good. Now let me copy that equation to correct. Yeah, table number 2. All the calculation you have to do that way, right? Inverse calculation. That make sure you correct that all of them. Okay. So that's the equation for the RCal, R equivalent calculated value. Good. And then this one is actually showing you R equivalent measured value. So let me copy paste that to here. This is R equivalent measured values. Okay, good. Any question? Yeah, that's good point. There's a table number 2. Small error earlier. Make sure table number 2 is a parallel circuit, and then you do all the calculation inverse addition. Okay, otherwise you will get a completely wrong answer. Yes, correct. Yeah, that's right. Yeah. So when you do actually this one, you can consider this is known. Because of that, you need to do another inverse addition of last one. Yeah, you can do that way, or you can copy paste this one directly here to this one, and then you go here and then do another addition of the other cell plus another new parenthesis 1 over third cell, and then close that parenthesis, then hit enter. Now you have a new number. You can see now if you have a parallel resistance adding again and again more into the circuit, your total resistance should be decreasing. Okay, that's very important. And also this one we can do the same way, copy paste this into here, and another parenthesis here, new parenthesis plus new parenthesis 1 over 35, right? 1 over 35, close that parenthesis, hit enter button, so I get a new answer. And let's do this with up to 3 significant figures, otherwise you will not see any errors at all, right? So if you have 2 significant figures, it look like the same, but up to 3 significant figures, I would assume there should be error. Yeah. So do this into 3 significant figures, okay? Always. Now let's copy paste these 2 equations. Please make sure you correct your table number 2. If you did with the previous addition directly, that is not the right way to do. That's a parallel addition, okay? Parallel case, addition should be inverse addition, 1 over and everything. Okay, that's the two equation you need for this one. Make sure when you're doing this lab report, don't put the equation directly into your table. Okay, some people did that last time, but your table looks ugly then. We don't really, because what you're practicing here is actually, one other thing you're practicing is actually how to make a report, right? How to make a nice report. That will be part of your job anyway. It doesn't matter which field you go in. So because of that, please make sure you practice accordingly. So when you're making the real report, all the tables should have only calculated result, and then all the detailed information, put it into appendix. So in our case, that will be appendix C, okay? All right, now you should get percentage error because of this different. Let's do that. Equal sign, ABS, parentheses, difference between these two, and divide by average between these two, adding these two together. Adding these two together, divide by 2, multiply by 100, 0.04. 0.18, yeah, there should be another parenthesis should between these two, okay? This point also, I think I missed that parenthesis. Okay, good. So any question so far? Let me copy paste this formula too. That's the absolute error calculation equation right here. Okay, that is a PD for table number 2, case number 2. Okay, good. Any questions so far? That's very good point. Please make sure you complete table number 2 properly. Okay. And then formatting you can do later, right? You have to make sure all these lines are visible. Some of you putting the table without those lines into your all the border lines to your word report, that is actually not look nice. Then you have some numbers randomly everywhere, that is actually looks very bad your report. Okay, so make sure all these lines are visible. Formatting is nice before you copy paste the table into your report word file. Okay, good. Any question? Everybody okay with that? Okay, then let's go back to the table number 3 then. Table number 2, number 3, we done case 1, right? This is our measured calculated. So all the, I think, functions also done there. So we need to make now table number 3, case number 2. Table number 3, case number 2, what we need, all these values are the same, okay? So the values are same, only difference for that is actually R3 is actually come to the top line, R2 goes to the last line, okay? That's the only difference because R1 and R3 must be serial, R2 should be parallel, okay? That's the difference. So let's make that one. Okay, you can keep the circuit as it is, get rid of this one, R3, and then get rid of R2. Get rid of R2. Okay, R2 should come here. R3 should go there. That's all really very simple change. All right, then we have the new circuit. That's all really. Okay, again the same way. I need the voltage across each resistor, right? Voltage across R1 is now 3.6. 3.6 voltage across R2 now. R2 should be right here now on the third line, okay. that is 25. Sorry, that is 12 volt, and across R3 that is 8.4. Keep remember that if you're working on the second case, R1 and R3 are serial now, okay? So you can write it down, that information here, to R plus and R3 directly, and then parallel with R2, okay? Parallel with R2. So that's the case number 2. So that's important because the way you calculated later will be changed everything. So then we need the current across R1 is 0.24. Current across R2, which is on the third line, 0.48. 0.48. Current across R3, which is now again on the second line, which is 0.24. Then we can do the voltage and the current to get all the resistance values, right? Voltage divided by the current, 15, 25, and 35. Okay, good. Any question so far? So I'm getting the right numbers there, right? So make sure you format everything accordingly, right? So I need at least 2 decimal places for each case. But some places you can see there's more decimal place appear, then you have to go back and reformat, decrease 1 decimal place, then you're going to get 3 significant figures correctly. I need only 3 significants, okay? Good. Now our measured equivalent again by using the total voltage and the total current in the circuit, right? Now total voltage is 12 and total current is on the very top line, okay? That 0.72. Okay, 16.7, 3 significant figures. Now R equivalent. Now you have to do the calculation. Equation is right here. Only difference is that it's the same previous equation. Only difference is now R2 and R2 flip. Okay, you can copy paste the previous equation. That should be fine. Then you readjust. Now you can see R3 should go into the first line. So that means 25 should be changed into 35. And then 35 on the other side should be changed into 25. Otherwise, equation should be about the same. Good, any question? So you will get exactly perfect result. So as a result of that, the percentage error now will be 0. Make sure you reformat everything to show 3 significant figures. Okay, good. Any question? Good, no problem. Anyone have any problems, correction? Make sure you take in the screenshot for each case, okay? I forgot to mention during the last circuit, but I think if you don't have it, you can quickly change this R2 and R3 and then take another screenshot. Make sure all the values are visible and then take the screenshot. When you take in the screenshot, add these 2 probes of the voltmeter at least to 1 resistor to show the value there too. Then it's a nice circuit showing all the values. Then you can take the screenshot. Okay, question. And also you can check always how the circuit symbols look like by clicking the symbols your right hand side very lower. You can change the whole circuit into circuit sign, or you can keep it as real life scenario. Okay, question. Good, no problem. Okay, let's build the last circuit then. So the last circuit is the Winston bridge. So we need 4 resistances. The values should be accordingly with this one, right? So let's build that circuit then. So let's get rid of all of these. If you click this right hand side very lower, you can see a small yellow circle. If you click that, it will reset everything, right? That's the easy way to get rid of everything. Let's bring now new 4 resistances. I need one resistor here, another resistor here, and another resistor here, and another resistor here. 4 resistances. Okay, and then in between these 4 resistances, let's put a bulb, light bulb right here, because we interested actually between the resistances, what we interested to see is 0 voltage, right? So if there are 0 voltage, there should not be any current passing through them, then I should not see any lightning up on the bulb, right? That's why. Then let's complete this circuit. These two should connect together, and the other side should connecting together, and then these two ends should be connecting to the battery, and I need a switch here, right? Apply battery and switch. We'll apply ammeter also to here to see the total current passing through the whole circuit. Okay, all right, now that is our circuit. Now let's connect this light bulb here in between the circuits. Okay, good. Now you have to adjust these resistance values, right, according to the given values. 25, 68, 37. Okay, this should be 25, 25. Second one should be 68. 68. And this one should be 37. Okay, so those are the given numbers for the case 1. Okay, we're doing 3 times this circuit, 25, 68, 37. Now, after you finish adjusting all of those, if you switch on this one, then you can see current passing through every segment. You can see the current passing through the bulb, right? So the light bulb, let's decrease that ohms value. Then you can see more current passing through there actually. If you decrease the value, you increase the value, you can see less and less current passing through there. Good, any question so far? Let's keep 10 ohms, that doesn't matter. So you can see the light bulb is lighting up. This is small yellow line appear around the light bulb, right? That actually represent bulb is actually lighting up. Okay, now circuit working fine. So now the idea of the Winston bridge is that if I adjust the R4 value, then at some point I can actually make voltage across this light bulb is 0. When voltage across light bulb becomes 0, then you should not see any electron passing through that line. Okay, that's the idea. Now let's adjust this. Let's change this value and see at what point we will see light bulb is actually becomes 0. Now you can see electron passing through that line becomes more and more slower and then slower and slower. At some point, that yellow line appear around the light bulbs becomes almost vanishes, right? But I can't see exact point. The good way to measure that is bring a voltage and then voltmeter, put the voltage probes on these 2 points and then measure the voltage and then change the resistor of R4 until you see exactly 0 voltage, right? Now it is negative means I have to go backward. I have to make it 0. 0.4, 0.2, 0.10. Okay, that negative positive doesn't matter. That just because of this probe, you can change that. So, but that should be zero. When that voltage zero in between those 2 points, then that is called the balancing point of the Winston bridge. At that point, there should not be any current passing through. If there's no any current passing through, you can apply the Ohm's law and you can build that equation which we discussed earlier. So let me go back to that and then build that equation for this circuit. Anybody have any question with the circuit? Case number 4, table number 4. Okay, let's take a look what we're doing here on this circuit. Okay, now you have a circuit look like this, right? So even I have one resistor here, another resistor here, another resistor here, variable resistor here. R4 is a variable resistor, and then we have a bulb here. I'm going to put a voltmeter here, right? So then you have external battery, power supply, and the switch. It is VDC and switch. Now, if you change this R4, by changing R4, let's put this number, letters here, A, B, and then CD. By changing R4, we can make VC equal to VD. At that point, I can write an equation, Ohm's law equation for these two, R1 and R3, right? So because you can see if VC equal VD, then VAC must be equal to VAD. VAC is actually current passing through there. VAC, let's say I1 times R1. Current passing through here, let's say I1. This, let's say I2. Total current into the circuit is I. And current passing through AD is I2 times resistance R3. And on the other side, you can say VCB, which is equal VDB. Applying same Ohm's law, I can write current is same everywhere on this line, okay? Same current on this line. I1 times R2, which is equal I2 times R4. Now you divide these two equations, right? So if you divide those two equations, I1 R1 is equal I2 R3. Everything divided by I1 R2 is equal I2 I1 R2 is equal I2 R4. And by dividing that current cancels out, then you will get R1 over R2 is equal R3 over R4. So that's the equation we're going to use to calculate the value of R4. R4 calculated value I can find R2 times R3 divided by R1. That's the calculated value, okay? Good, any question? That's called the balancing point of the Winston bridge. Okay, whenever this is table number 4. Table number 4. When the Winston bridge is balanced, then the voltage C should be equal to voltage D. That's the point. Okay, so when it is happens, then I can figure out this equation. Okay, question. Now in the experiment, what we're going to do, we can actually measure that R directly, right? The number needed, you can see number needed is 100.5. We're going to compare that one exactly the number we're calculating. So that's all really. Okay, question. Everybody okay with that? Okay, then let's continue. Table number 4. Table number 4 is completely different, so I would suggest you to build that table completely from scratch. Don't copy paste from the previous table. It's not meaningful. Table number 4, we're doing the Winston bridge. Make sure you name it properly, okay? Winston bridge analysis. Princeton bridge analysis. Okay, then column 1, I need all the R values, right? R1 equal 25, R2 equal 68, R3 equal 37, R4 is unknown right now, okay? R4 which is unknown. Let's see what happened here. R2 which is 68, R3 which is 37, and then R4 which is unknown. Okay, that's unknown. That we have to figure out by doing the experiment, right? R4 calculated, now you have to do this equation, right? I show you the earlier equation here. R4 calculated going to be R2, R3 divided by R1, right? Let's do that calculation first. R4 calculated, let's add another column here. And this one going to be all the resistance values. Resistances. And then this is R4 cal. Then R4 observed on your experiment. So R4 cal going to be equal sign R1. R4 calculated is R2, R3 over R1. Okay. Let's do that calculation. R2 is 68 times R3 is 37 divided by R1 is 25. So I'm getting 100.64. R4 observed is actually, what's the number you get on your circuit whenever the voltage is 0? Number is 100.5, right? So let's do that 100.5, and then observed value is up to 4 significant figures, which means there's no meaning having more significant figure on your calculated value. Change that. So the everything into 3 sig figs, okay? You can highlight everything into 4 sig figs, right? Which means 1 decimal place. Or you can convert it into scientific notation, that also fine. If you do in scientific notation, make sure 4 significant figures. Okay. Then you have to do the percentage difference, right? The same way, equal sign, ABS, parentheses, difference between these two. And divide by average between these two. 2 parentheses, adding these two together, divide by 2, close that parentheses, multiply by 100. And that also we need same amount of significant figures. So let's do 3 decimal places, then I'm getting 4 significant figures. Okay, but what matters is number of significant figures in measured values, right? That's what the point of the experiment, right? Always your any calculated result should go with the measurable lowest significant figure value, right? In this case, measurable value, what we're measuring is resistance value of R4, that is 100.5. Okay, question. Everybody got that? Any question on that? Another way to measure this accurately is that you can either measure voltage or you can bring the current sensor and then place it here to see whether the current passing through is 0, right? Either way is fine. Or you can put the ammeter directly across these 2 points. That also should be working good. So I can put ammeter across these 2 to make sure there's no current passing through here, okay? Let's disconnect this one and then let's connect the ammeter across that. There's various ways to adjust this, okay? I need more space here. All right, then let's bring another wire and then put the ammeter there. Okay. Now you can see if I change this resistance into a different number, you can see current passing through that line, right? And then as a result of I'm changing this resistance, at some point, current passing through the midpoint will become 0. That's the exact point we need, okay? See, that number can be slightly different because current passing through there should show a 0 when it is very close to 100. Okay, 98 now. Then let's take a look the voltage across that. Still you have a small voltage. See the difference right now? That's the problem. If you use in the ammeter there, still you will get large error, right? Calculated value is 100, remember? But now I am getting current 0 at 98, which means our ammeter is not sensitive enough. So that's the problem. So which means using the ammeter to measure that will not be a good idea. I have to use the voltmeter actually. So see, small voltage is still there. I have to change this resistance until I get voltage really equal to 0. That's the point. If you do that, then that number is very close to the calculated value. See that? Make sense? Everybody see that difference? Good, any question? Okay, there's various way to do that, but the best way is that actually you have to use the voltmeter, okay? Now only difference for the next two is that you have to change those numbers R1, R2, R3 to with the given numbers, that all. For the case 2, R1 is same, R2 and R3 are 85 and 45. So keep the same circuit, R2 change into 85, 85, R3 change into 45. Different values, and then now you can see voltage again becomes visible, right? And you can see the ammeter also show you a number. Now again you have to click the R4 and then change the value of R4 until you get voltage 0. $25, 85 and 45 seems to be, I can't get the voltage 0 at all. Yep. So I have to change those numbers a little bit. Okay, there's another way to do that. Get rid of this resistor here, fourth resistor. So if you go down here on your right hand side, you can bring the larger resistance value. And let's try with that one. Larger resistor, that I should be able to change large numbers above 100. Yeah, so you have to change this resistance into a larger value, okay? Yeah, so right hand side selection tool, click the down arrow, then you will get a different type of resistor. You can see the symbol is different. That resistor you can go above 100, okay? Previous resistor, these symbols with the 4 lines, you can't go above 100, okay? You have to bring that new resistor here and then replace that with the R4. Now you can go above 100. Now change it slowly. So only problem is there, you can't go small numbers. Yeah, you can't go with small numbers. That will be a problem. The best way is that adding two resistance together. Yep. So let's do that. Let's add one more resistor here. You need more spacing here, right? You can actually expand this line right here. Make more space. This should be connected here. Let's add another resistor here. Then I have R4, which is actually combined effect of these two, right? Adding together, first one is 100. Second one, let's change slowly to see whether voltage is actually become 0 at one point. Should be close to 100. Yep. You can go all the way to 120. Now let's increase this one slowly. Okay, as you see, it increasing voltage becomes 0 at 33, around 153, correct. Okay, good. Now that circuit you have to work around. Okay, there's a little bit of work to do there because not directly putting everything together, not directly working. Okay, make sure all of this visible before you take a picture. Not the current 0 point where we are interested because the ammeter seems to be not sensitive enough. You have to have the voltmeter across those two. Okay, then take a picture, then complete the second line right here. Second line, only difference is that same calculation. Okay, so let's copy paste this one here. So the same calculation, only difference is that the second one is now 85 and 45, right? 85, 45. 85, 45, measured value I'm getting 153. That's what I got. You can write it down, the number you see. Okay, R3 is 45. Let's do this calculation then. Calculated value going to be 68. R2, R3 is 45. Divide by 25. 85 times 45 divided by 25. 153, and the resulted calculated value, measured value, I got 153 exactly. Okay, good. So adding these 220 and 33, 153. Okay. And for the last case, what we need is resistance values now different, 25, 115, 55, right? Well, first one keep the same 25. Second one should be now 115. 115, and the third one now is 55. Third one should be now 55. Okay, now again, now you can see there's a voltage up here, which means I have to change the resistance on R4. Let's first get rid of 1 all the way to 0 and then see whether I can get the resistance from 1. Not possible. I need both of them. Change the second one on the fourth resistor until you see 0. It seems to be 2 is not enough, which means I have to add another, right? So it's not a problem. So expand this one. Bring another new resistor here. Add it serially. And then connect this one. Now your fourth resistor is all of these three together, okay? Okay, change the last one slowly until you see 0. Okay. That's the place we got 0. Adding all of these three together, 120, 120, 240 plus 12, 252. Okay, that's the last one. Let's do that calculation. So the last one, your values are different. Okay, so these two calculation will be different then. Copy paste here. All right, now this when you do this calculation, R1 is same 25, but R2 is now 115. 115. Now R3 is 55. Okay, that's the only difference. Okay, then do this calculation again. R2 times R3. This should be 115 times 55. Divide by 25, I got 253. If I add all of these three together, I get 152. 252, slightly different, but it's close enough, 252. So the percentage error is 0.396. Okay, good questions. So we completed all the tables and all the calculation. Okay, so you just need to copy paste all the tables onto your report and then complete the report accordingly. Make sure before you copy paste the tables, all the formatting is done correctly and then so on. Okay, good. Any question so far? Everybody okay? No problems? All right, then let's take a break and then we'll start in 15. Okay, in 15 minutes. Which means right now 10:10, 10:25.